in order to know how to use the first law of thermodynamics energy equation, we have to know sort of which energies are going to be used. So first law of thermodynamics, of course, says energy can't be created or destroyed. It can only change form. So the first law of thermodynamics really, in its simplest form, just says any energy that goes in would be the same as the energy that goes out. But we should really know what types of energy could be going in and what types of energy could be going out. Well, if I look at a closed system and I put, say, a mixer in that system, I have a fan and maybe I paid for some electrical energy to turn that fan. My first step of thermodynamics problem is going to be defining a boundary. So here I have a system and the surroundings of this system, and I can observe that by turning on this fan, I can add kinetic energy to the system from its surroundings. To system from surroundings. Kinetic energy is 1/2 times mass times velocity squared, but we won't get to that yet. I just want to take a look at the types of energy. Another type of energy that we are familiar with is potential energy. Potential is the energy that is inherent in because of a change of height, and the effect that a change of height can have on a mass when gravity acts upon it. So I just drew a simple system here where there is a height difference between inlet and outlet. This is the in, this is the outlet. And the difference between the inlet and outlet is marked with h, the height. And in this system, I'm going to have some mass flowing in because I'm making an open system. This was a closed system. I'm just illustrating a few different types of energies that we think are obvious in these systems. Mass will flow in, mass will flow out. I don't see it going anywhere else. So it's the same mass that flows in and out. But as that mass flows through, there must be some potential acted upon or added to that the system because of that mass going through a change in height. So here, potential energy, and of course that's a function of your mass times your gravitational energy times your height. So I would call that the potential energy. We are adding potential. Just by offsetting the inlet to the outlet, we add some potential energy to this system. So in general, there are lots of different types of energies. There's thermal energy. We usually call that Q. There's mechanical energies. Oops. There's mechanical energies, which we usually call work, the ability to do work. We have our kinetic energy, which is our function of velocity and mass. We have potential energy, which is a function of height and mass. There's electrical energy, also measured in joules, magnetic potential energy, chemical potential energy, like the joules that exist in a peanut that you eat that become calories or joules inside your body after that. That's a type of energy. All energies are measured in joules. They can convert between one another. Nuclear energy. Nuclear energy can be converted into thermal energy and be quite useful. So all of these different forms, and that's not even all of them, contribute to the total energy of a system. All right, so we are never going to be really calculating the total amount of energy in the system, but we're going to be dealing with the changes in those energies from one side of the equation to the other side of the equation. Okay? We can further discriminate forms of energy into what's called macroscopic and microscopic forms of energy. Macroscopic ones deal with are referenced to an outside reference frame. So the kinetic energy and the potential energies. The microscopic forms are those that are related to the fluid that is sitting inside that system. So they relate to the molecular structure of the system, the amount of activity it has. When you add some heat to a system, then it's going to change the internal energy of that fluid, for example. And the internal energy of that system is denoted by U. So let's say I put this kinetic energy into this closed system up here, but I don't let any thermal energy escape. Let's say I insulate it. It's insulated, so no thermal energy can escape. Well, then I must have been heating up that system. So if Q dot equals 0, then I must have been heating up that system. Then the internal energy after some time must be must be bigger than the internal energy that we started with. So the internal energy of a system is basically what you can make the molecules be more excited, so they inherently have more energy, and we'll talk about that again. We'll talk about that in a moment as well. So if I were to summarize sort of the major energies that go into this system, then I always start my thermodynamics problems with E in equals E out. I would say there's already an inherent internal energy of this system. Then I maybe added some kinetic energy. I might have added some potential energy, and that'll be equal to the final amount of internal energy in the system, plus kinetic energy left over, plus potential energy left over in the system. And that would be our first law, energy balance for any thermodynamic system. Again, let's look at it here. This just says E total. This says it the same way. This now rearranges this equation, and it says E total is going to be E U out minus U in plus E out minus E in minus or plus E U out minus U in. This is kinetic potential out in minus in. And the sum of all of those changes must equal to 0. This would be in, out, out. So this is it just written in a different way, where the total amount of energy is equal to the internal energy, kinetic energy, and potential energy, or change in that. And where energy kinetic equals 1/2 mv squared, we should all know that, and potential energy is mgh, height. I said Z here, but I like to say H. So these are the different types, the different forms of energy that can be substituted into our first law energy balance when we are solving a thermodynamics problem.